So let's start some illustration related to the theory of center of mass and the Newton's second law of motion correlation. So the first illustration in your textbook is given as the particle of mass m1, m2 and m3 are placed on the vertices of an equilateral triangle of sides A. So let me draw first the figure of such kind of representation and arrangement. So this is the representation in which I have putted the particles of mass m1, m2 and m3 on the vertices, and they are equilateral triangles. See, all are having the sides with lengths of small a. So we have to find out the center of mass of the system with respect to the position of particle of mass m1. See, I have considered the figure over here as M1 at origin. So this is my origin O. Also the particle of mass M2 is at the position A0. So this is my R2 I can say, and this is having my R3. So all these quantities are known full to me, and as the triangles are equilateral, so all are having the same angle of 60, 60 and 60 degree, and their total sum will be 180 degree. Now, first of all, my target is to find out the coordinates of particle with mass m3 because there only this is the particle whose coordinates are not known full to me. So, my first task is to find out the coordinate of the particle with mass m3 is, remember the max because the coordinates are given like the x-axis is or the x component a cos 60 degree and a sin 60 degree is equals to a by 2, and the other coordinate is under root 3a by 2. So this is the position vector of M3. So I am now writing all the position vector of mass M1, M2 and M3 containing particles as R1. So R1 is the position vector of particle having mass m1. So we have considered that at origin. So R1 is equals to 0, 0. For the position vector R2 of mass m2 containing particle, so its y-axis is 0, but its x-coordinate is the side small a, and the third position vector is a by 2 and under root 3 a by 2. Now, according to the definition of the position vector of center of mass, so is given by the equation, and the equation is RCM is equals to M1 R1 plus M2 R2 plus M3 R3. But why we have taken only up to 3 over here? Because it is the system of only 3 particles, and at the below M1 plus M2 plus M3. Now I am substituting the values of position vectors wherever it is applicable. So M1 into 0 0 plus M2 into A0 plus M3 into what is the value of that position vector R3? It is A by 2 and under root 3 A by 2. This whole term is divided by M1 plus M2 plus M3. Now simplifying such a relation, so what you will get? The M1 is multiplying inside, so it is 0 0. Now M2 I am multiplying inside, so it is M2A and 0 plus M3A divided by 2 and root 3 M3A whole is divided by 2, and this term is also divided by the total mass of the system M1 plus M2 plus M3. Therefore, finally my position vector will be, now see, this is nothing but the vector type of addition. So I am just adding the x coordinate and y coordinate. So I will get M2A plus M3A by 2, comma, see this is 0 0 and root 3 MA by 2. So I can write down simply as root 3 by 2 M3A, and this is divided by M1 plus M2 plus M3. So this is the actual relation, but what should be the x coordinate and y coordinate actually? So we can write down this term is totally divided by total mass, and this term is also totally divided by this total mass of the system. Therefore, my center of mass is, I am taking A as common from the x coordinate. So this is M2 plus M3 by 2 into A divided by M1 plus M2 plus M3, comma, under root 3 by 2 M3A whole term is divided by M1 plus M2 plus M3, and here the bracket is over. So this is your x coordinate of position vector of center of mass of the system, and this is the y coordinate of the position vector of the center of mass of the system. So with this our first illustration is over. Now we will move on to the second illustration. So the illustration number 2 is given in your textbook as, in a system of 3 particles, the linear momenta of the 3 particles are given as 1, 2, 3, 4, 5, 6 and 5, 6, 7. So here the momenta of 3 particles, so I am denoting the momenta of the first particle as P1. So it is 1, 2, 3. The momenta of the second particle is P2, which is 4, 5, 6, and the momenta of the third particle is given as 5, 6 and 7. Now These components are in kilogram into meter per second. So, this is also kilogram into meter per second. Here also kilogram into meter per second. And this third momenta is also of the type kilogram into meter per second. But one another quantity is given to you as velocity of the center of the mass of the system. That means VCM vector is given to you, and this velocity vector is given to you as 30, 39 and 48, and these are the component in meter per second kind of unit. Now, our target is to find out the total mass of the system because this quantity is unknown at the present. So, which kind or what type of relation I can use over here? So, this is the relation which we have obtained in the second theory as T is equals to mvcm. Now, this P is the total momentum. Therefore, P1 vector plus P2 vector plus P3 vector is equals to mvcm vector. And this P1 is written as 1, 2, 3 plus 4, 5, 6 plus 5, 6, 7 is equals to m into 30, 39 into 48 meter per second. Now, if I am multiplying this m inside the bracket and I am co-linearly adding this vector type of addition, then my answer will be, see this first component 1 plus 4 plus 5, so 5 plus 5 is 10. This 2 plus 5 plus 6, so 2 plus 5, 7 plus 6, 13. Similarly 3 plus 6 plus 7 is 16. And simultaneously on the right hand side it is 30m, 39m, 48m. So now I am comparing the components of left hand side and right hand side. Therefore, the first component was 30m, means x component is equal to 10. That implies from this we are getting the value of m as 10 by 30. So it is 1 by 3. Similarly, the y component was 39m is equals to 13. So here the m component is 13 divided by 39. So it is also equal to 1 by 3. Therefore, 48m is equals to 16, and that is also equal to 16 upon 48 is equals to 1 by 3. So, from this the value of m is coming out as the same. So, my total mass of the system is 1 by 3 kg. So, this is the final answer, and with this our illustration number 2 is also over. So, let's move on to the illustration number 3.